record. All right, well, welcome everyone. Thank you so much for coming to this math talk. As well, there he is on the screen, right? Jim sends his condolences. He wishes that he could be here, but there's a water heater problem at home that he is taking care of right now. So I just want to introduce our speaker, Freeman. He will be giving a talk on the hardest problems in the hardest competitions.
But you can still see this. Jim, you can still see this?
Yes, I can.
All right, hey everybody, I'm Freeman and I'm a big fan of contest math. When I was an undergrad, I took the Putnam. For those of you who don't know, the Putnam exam is generally considered the hardest undergrad mathematics exam out there. There's 120 points in total, and usually a score of 1 or 2 is considered good. All right, so that's what gives you some idea of the difficulty of problems we're talking about. They're not just difficult, they're difficult for mathematicians who are used to difficult problems. So this talk is going to be really 2 parts. I want to talk about 2 big ideas: clever and difficult. I've written problems for the Clemson Calculus challenge for the past 3 or 4 years. And these are the 2 things that I try to keep in mind when writing a problem. I want them to be clever or I want them to be difficult. And I'll explain more what I mean by that. Let's look at an example of what I consider to be an exceptionally clever problem. This integral from 0 to 1, x to the 4th, 1 minus x to the 4th, divided by 1 plus x squared. This showed up on the Putnam a good long time ago, and it's actually not considered a difficult Putnam problem. In fact, it's really not a difficult problem at all. The idea here is you perform polynomial division, okay, standard. You end up with a polynomial, and the last term is 1 over 1 plus x squared. Well, okay, when you take the integral from 0 to 1, you end up evaluating a polynomial and arctangent. So then when one actually computes this, it does all the algebra. Why be 2 over 7 minus pi? Now that's a pretty cute result, right? 22 over 7 is a commonly used approximation for pi. If there's any engineers in here, they'll know that in fact the 2 are equal, but let's not worry about that right now. The problem on the Putnam didn't really ask to solve the integral. It was more clever. It asked to interpret this principle. Okay, let's take a look. Something to the 4th, something to the 4th, something squared over this positive region. This integral is going to be greater than 0. So the interpretation here is that this approximation for pi is actually an overestimate, which is not at all obvious from this. Like who would have guessed that, right? Just from looking at this integral. So I consider this to be a perfect example of a clever problem, but one that's not really difficult. I'm not going to prove it here. You can prove it for yourself if you like, but it really is as simple as polynomial long division. This is what I think is a pretty good example of a difficult problem, but not particularly clever. This is from the 2022 Clemson Calculus challenge. It was the last problem on the exam, so ostensibly the most difficult, and it was written by yours. Okay, so integral 0 to 1, the cube root of this polynomial. The reason why I say difficult isn't because it takes up 50 pages of integral work. Let me tell you what I mean. Right on the board here. Somebody give me a natural number. 3 larger. 51. 51. We'll take the 51st derivative. Somebody give me the trig function. Come on, I know y'all know trig. Someone give me a trig function.
Cotangent.
Cotangent. E to the x plus 1 of x. What goes inside is equal. Who would agree with me when I say this is a difficult problem? Yeah, I'm seeing people nod. But it doesn't have any soul. Yeah, it's a difficult problem, but there's a part to it. You're just gonna spend 100 pages of tedious work writing out the derivative, and then at the end, wow, you just have a gross answer. So that's what I want to avoid. There's difficult, like tedious difficult. This sort of difficult is more insightful. You could spend hours, all the tricks in your toolbox attacking this problem, but unless you see the trick, that's not gonna break. What tools do we have in our toolbox to evaluate a polynomial under a cube root? Yeah, that's right. I don't know. That's why I wrote this problem, is because it's difficult to attack. You have to see it. So I'll just go ahead and bury the lead a little bit, put a fact up there. The integral from a to b of f of x is equal to the integral a to b f of a plus b minus x. It's not difficult to prove the substitution is exactly what you would think. You substitute a plus b minus x. Well, if we apply this to this problem, what should we substitute? 1 minus x. Well, okay, let's go ahead and do that. So we have this polynomial. Traditionally, we would do like x equals 1 minus u. I'm not going to worry about that too much. Just everywhere we see an x, we're going to plug in instead 1 minus x. And then we'll do all this algebra. We don't have to worry about the bounds of the integral. We don't have to worry about dx because we saw from our fact, doesn't matter. They're going to be equal. End up doing lots of algebra, end up with, does that look familiar? What is that last value? It's the negative of what we had before. Well, wait a minute, this polynomial was under a cube root. We know that we can pull the negative out. In fact, we can pull it all the way to the front of the integral. Assuming this integral is finite, we have a natural number equals the negative of that natural number. What's the only real value that equals its own negative? 0. So this integral equals 0. Now this was okay. Perhaps it's not all that wild when you just see the proof like that. But this is really quite a resilient problem. A lot of the tools that we have, trig substitutions, trying to factor it, partial factor expansion, they just don't work here. This is the trick. All right, now let's put these ideas of clever and difficult, open parentheses, insightful, close parentheses, and put them together. This is, I think it might be right now my favorite problem. So it's the integral from 0 to infinity of 1 over 1 plus x squared times 1 plus x to the alpha, where alpha is some positive real. This showed up on the Clemson Calculus challenge last year. I think it was also problem of the week at some point. Our idea of taking the a plus b minus x doesn't work here because you have infinity, right? That's just what's another simple substitution that we're used to that will preserve the bounds of 0 and infinity? The simplest substitution you can think of. 1 over x. 1 over x. Well, okay, let's see where that gets us. Let's plug in 1 over x. So then du equals negative 1 over x squared dx. All right, we take this, plug it in. These bounds have flipped, but it's actually not a problem because this negative here, the derivative, you can just tuck it in there and it'll flip those bounds back. This u squared was a little awkward, but we can distribute it into the 1 plus 1 over u squared. And what do we get? Yeah, I'm seeing people nod. You're starting to get it. They'll turn that into 1 plus u squared. Well, okay, let's do the same trick for this 1 over u to the alpha. So we'll multiply u to the alpha divided by u to the alpha. We'll end up with this. So this is the exact same integral up here, except now we have a u to the alpha up in the numerator. Okay, cool, who cares? Where did that get us? Here's the trick.
Alpha 1 minus 1.
Yeah. What happens if I add these two integrals? What will I get up in the numerator?
Alpha 1 minus.
If I take this integral and add it to itself, where the second one is the substituted value, or we substitute that 1 over x. Well, now when I add these together, they have the same denominator. So we can just add them straight across in the numerator, we get 1 plus x to the alpha. Well, wait a minute, there's the same thing in the numerator and the denominator. So we can cancel. We know this integral, arctangent, ends up being pi over 2. So overall, we get that the integral as a function of alpha is pi over 4 regardless of what alpha is. That's pretty sneaky. This integral was first handed to me without comment in this form, where they use specifically the value of alpha equals pi, the golden ratio. Who here has seen an integral with the golden ratio? Right? Like it just doesn't happen. And not only that, we have phi and it somehow relates to pi. Like those are like my two favorite constants. Wonderful. It turns out it's kind of trivial. You can replace phi with anything. 2, 4, a million. Let's take this same idea, try on this one. This one was from a relatively recent Putnam exam, and is generally considered to be one of the more difficult integral problems that come out of the Putnam. So integral from 0 to pi over 2, 1 over 1 plus tangent of x to the power of root 2. Oh, okay, I'm sure we'd like to try some trig substitutions, or maybe even like a Weierstrass substitution if we're feeling particularly clever. But that root 2, that's the real problem. Any substitution we perform in here, it's still going to have that root 2 power, and that's just going to screw things up. If we think back, I gave you a fact about a substitution. What was it? There go on. I said the fact of the integral a to b f of x is equal to integral a to b of
A plus B minus A.
exactly. What do we get if we try that here? Yeah, right. So we'll want to substitute pi over 2 minus x. Well, now I have to do a little bit of thinking. Tangent of pi over 2 minus x. Well, we know tangent is sine over cosine. Does anybody remember a half period shift of sine gives us
Cosine or negative cosine.
yeah, right? It's one of those. Turns out to be cosine. So then, okay, you might logically guess the same thing happens to the denominator. Cosine half period shift gives us sine. Turns out this is correct. Cosine over sine. I feel like you have a word for that. This is cotangent of x. So what the substitution of pi over 2 minus x gives us is, this is exactly the same integral, we just replaced tangent with cotangent. And again, like before, cool, but where does that get us? Here's the trick. We add this integral to itself. All right, well, we could think of this as a fraction. 1 over a plus 1 over b, they need a common denominator. So we'll multiply on the left by 1 over 1 plus the cotangent, multiply on the right by 1 over 1 plus tangent. We'll add the 2 on the top, and we get. Okay, well, great. Again, it seems like we haven't gotten anywhere interesting. Watch this. Let's FOIL the denominator. 1 times 1. Yeah, that's right. I thought the same thing. Yeah. Okay, 1 times the cotangent. Cotangent, tangent times 1. Tangent. Tangent times cotangent. 1. So, okay, let's write that out. Yeah, on the top we have 1 tangent, 1 cotangent. On the bottom we have 1 tangent, 1 cotangent. Just like that, like a thunderclap. It all just disappears. So this integral, 0 to pi over 2 of 1. Okay, not too bad, that's pi over 2. So it turns out that this integral equals pi over 4. Okay. But here's the thing. That root 2, what role did it play? Yeah, it didn't show up anywhere. It was effectively pointless. We could have replaced it with alpha. And actually proved it, not to myself anyways, but I have a sneaking suspicion that this integral is the same one we saw before. The 1 over 1 plus x squared times 1 plus x to the alpha. So I hope you're starting to get an appreciation of the power of adding an integral to itself. It sounds trivial, but it really shows us that these problems have straightforward solutions. I mean, I've put the entire solution for all the problems so far on like a slide. That doesn't sound like a difficult problem, but the difficulty is seeing the right substitution and seeing you should add it to itself to get things to cancel. This is a fun one from the IMC International Math Competition. This was from 1998. The IMC is known for their very difficult problems. And this one is a functional equation. So I want to show you that this doesn't always have to be an integral, solve an integral. This one is let f mapping 0, 1 to the reals be a continuous function such that x times f of y plus y times f of x is less than or equal to 1. We're asked to show that the integral from 0 to 1 of f is less than or equal to pi over 4. This is usually how functional equation problems look. They give you some relatively unassuming inequality or equality, and then show that magic happens. To me, it is not at all obvious that this symmetric inequality gives us any sort of bound on the integral. In fact, it's almost even hard to believe. Surely, this functional equation is not that restrictive. Well, all right, let's keep in mind what we've been doing so far. Make a substitution and then add the integral to itself. This time I'm not going to ask you what the substitution is because I don't think it's obvious at all, which is why this is a clever and difficult problem. That's exactly. The first substitution is sine with the derivative of cosine. So then when we plug this in, integral 0 to pi over 2 cosine times f of sine. That kind of looks like an x times f of y. So then the natural idea, if we substitute sine and get this, maybe we should substitute. Maybe we should substitute cosine. Yeah, let's see where that gets us. It's a little bit more difficult because now we have this negative and the derivative to deal with, but it actually turns out that's a good thing. This allows us to take these two bounds and now swap them. 0 to pi over 2 instead of the other way around. Add an integral to itself. Well, wait a minute. When we do that, we'll get something of the form x times f of y plus y times f of x. We already know how to use it. That's bounded by 1. So adding this integral to itself gives us pi over 2. So then we've shown that this function, which had a, I don't think, a very restrictive functional equation attached to it, turns out the integral is bounded by pi over 4. Not obvious. This one I put last minute, wasn't actually planning on presenting it, but here it is. I'm pretty sure this is an Euler classic. I think they put it on the Putnam as well. So the integral from 0 to pi over 4 log of 1 plus tangent of x. Okay, well, sort of like the ones we've seen before, turns out this one is a tough nut to crack. We try to do, say, tangent substitutions or Weierstrass substitutions or something like that. This log causes problems because any substitution we make will be changing this dx into, say, du, but we won't be able to bring it in because the log prevents us. So most of these substitutions just kind of end up nowhere. At the very beginning, I gave you a fact. Integral a to b of f of x equals integral a to b of. Yeah, I'm gonna make you say it again. Come on.
F of a plus b minus x.
Yes, sir. So what happens if we try that here? Okay, we'll sub pi over 4 minus x into tangent. Where does that go? Little fact we need to recall. This actually pops up a decent amount on contest math. The tangent of a plus or minus b is equal to the tangent of a plus or minus the tangent of b divided by 1 minus plus tangent of a times tangent of b. Okay, so if we do this with pi over 4 minus x, okay, well, it seems like we've just made a mess of things. But wait a minute, what's the tangent of pi over 4? Do you remember? Yes, sir. I actually usually think about it in the opposite way. I think of arctan of 1 equals pi over 4. But whatever. So this ends up with this actually very nice form. Tangent of pi over 4 minus x equals 1 minus tangent over 1 plus tangent. So when we substitute this in, really what it will look like is we replace the tangent with this. And then the bounds are the same, dx is the same. When we add this integral to itself, we get this log of 1 plus 1 minus tangent over 1 plus tangent. Okay, well, we want to somehow find a way to incorporate the 1 into this fraction. How do we do that? We can write 1 as 1 plus tangent over 1 plus tangent. When we do that, then these two fractions will share the denominator, and the numerator will look like 1 plus tangent plus 1 minus tangent. So it ends up with actually these tangents sort of disappear from the numerator. Why do we care? Where does this get us? Yeah, log of a over b equals log of a minus log of b. So it turns out, it barely fits on the page. We end up with this integral plus integral log 2 minus that same integral. So these two will cancel. Integral 0 to pi over 4 of log 2. So sort of like we've seen before, suddenly stuff just vanishes, and before you know it, you've got an easy integral to work with. So overall, we get that this integral is pi log 2 over 8. Not at all obvious. So all of these problems had two big ideas. Substitute, and then add it to itself. And then somehow, through black magic, stuff cancels, and then you end up with really just the integral of a constant. I'm giving you some homework if you want. Turns out all of these integrals are the exact same idea. They look intimidating, but once you sit down, you already know the tricks for them. This integral is, of course, an Euler classic. This one appeared on the Putnam. This one was a Lagrange classic. And this final one is a bit of mathematical folklore. It's actually popped up a handful of times. I don't think we know who invented it. Might have come out of Russia. My point is, all of these look very non-trivial. But you already know the trick. Sit down, give them a try, see what you get. All right, I think that's all I have for right now. I'll leave this up if you want to think about it a little bit. But as proof, solutions for all of them fit on a page. They're not difficult problems once you know the trick, and you do. So I'd like to thank you all for coming. I hope you learned something, especially about how adding a number to itself can be non-trivial. When you go out there and try a contest map for yourself, look for it. Because once you start looking for this trick, it pops up everywhere. Putnam, IMC, Clemson Calculus Challenge. So I'd like to thank you for your attention.
All right, let's go ahead. Are there any questions?
Kind of wonder what the intuition is behind that functional inequality, because that is really not obvious. Like I was trying to look at it, and I mean, that substitution does not.
Yeah, right, it's not obvious at all. Well, some intuition you can get, however, 4, a lot of the previous ones we saw were however 4 as well. So that sort of starts to give you some idea of what's happening here. Trig is happening in the background. But I agree that the idea of, oh, hey, this suggests we should substitute sine and cosine, not obvious at all.
Right, see, I was trying to think, now that we know what the substitution should be, you know, what would that look like? Sine X, F of cosine Y, and it's still not, yeah. Just looking at that cold, I think that might take some ingenuity to make that substitution. That's pretty wild, I like it.
So really what they were looking for you to see is that you should set y equal to x prime. I think of x as maybe say a function of t. So it's not clear, you're right. But that's sort of why it's there.
Right,
It's not
right.
clear what would be a good
Oh,
concept.
it's sort of to view one as the derivative of the other, essentially. Oh, okay, yeah. That's,
The problem also continued to ask for when do you obtain equality, which is a big thing that we worry about in analysis. Okay, you have this bound, do you actually achieve equality? Because otherwise it's not a great bound. And it turns out that there is a relatively simple function that attains this bound. I don't remember what it is. But it's possible to do. So this is genuinely a good bound. In fact, since we're talking about intuition, I wasn't thinking about saying this, but I guess I will. For these problems, I've left an Easter egg. One of those you've already seen before. I don't mean like it has the same value. I mean, it is literally the same problem, just a substitution away. See if you can spot it. Have any other questions?
I have a comment. I think, you know, these are really some pretty righteous tricks. I really like this, and it's right up there with the Feynman stuff too, you know. But there is an advantage that you have when you find a problem on the Putnam or, you know, one of these tests, and that advantage is you know going in that you can actually do the problem, right? So, for example, if you have something like e to the x squared, you cannot write its antiderivative down in closed form. You have to use a power series. That's the best you can do. And you certainly could solve the integral e to the x squared for certain values, right? If the integral is definite or if it's an improper integral. But, you know, if you encounter something in the wild, if a lot of these examples, if you change a 1 to a 2, you can't do it anymore, right? Like that first example you had with that cube root, if you change that last number by 1, then you're out of luck.
Yeah, you're right. That is a definite advantage. I'll even go further for things like the Putnam or the IMC. You know, there's going to be a trick. It's not just going to be, you know, like this example, tedious work, but it's also not going to be unsolved. There's something you need to see, some insight, or else they would put it on there.
Absolutely.
and sometimes when you see a random number, that seems a little bit bizarre. Sometimes you can substitute it with just anything.
Mhm.
So it's good not to get tangled up on, you know, if some square root of 3 shows up or something like this.
And that's sort of the same idea with these alphas. Like with the tangent problem, the 1/1 plus tangent to the root 2. Root 2 didn't play any special role.
Yeah, you can substitute alpha with anything and make the integral look even wackier.
Yeah. So if we wanted to, we could substitute like square root here, or this one even has quite a lot if you do like pi/2, pi/4, pi/6. But that just makes it unobvious how you actually solve it. Putting it as alpha, you're right, makes it a bit more clear that.
Right, you sort of, yeah, you get rid of something that's kind of wacky, because it usually won't play a factor anyways, yeah. I mean, maybe it will sometimes, but.
Well, right, you know, that you showed that one problem. I guess it was the integral of quantity 1 plus x squared and then 1 plus x to the alpha, right? And you said the first time you saw it, that alpha was actually picked to be the golden ratio, right?
Yeah.
And that's actually a red herring, right? Because you look at that problem and you think that the golden ratio plays a role and it doesn't.
I think the only integral that I know of that. It's not racing. I think the only integral that I know that involves the golden ratio non-trivially. The integral 1/1 plus x to the pi. That to the pi. I think it's from 0 to 1. I hope that's right. Might be 0 to infinity. But it turns out that this integral. Oh, I guess we should put the answer. Non-trivial equals 1. And the phi is genuinely necessary, but that's the only integral that I think I've ever seen that non-trivially involves phi. Fun fact.
Any other questions? Let's go ahead and thank our speaker again.
Yay.
I'll leave these up if anyone wants to take a photo, think about them later. I guess I probably should have done this earlier, but I forgot. This is the 2022 Clemson Calculus Challenge. The meant to pass around if anybody wants to take a look, but I'll just put it here if you want to see what the problems are on there.